Good afternoon, everyone. I'm Hao Huang, Associate Professor for Social Sciences, and welcome to the Illinois Tech Social Sciences Great Problems, Great Minds seminar series. For today's seminar, we will open the floor to questions at the end after the talk and lecture. Today's speaker, Dr. Yongwan Chun, a professor and the program head of the Geospatial Information Sciences program at the University of Texas at Dallas. His research interests are in geographic information sciences programs at the and spatial statistics methodologically, and line in urban geographic issues as substantive research areas. Specific research topics include quantitative methods, and especially using spatial statistical approaches for geographic research, geographic data uncertainty, population migration, urban crime, and public health. He has published 65 peer-reviewed journal articles in top journals, such as the International Journal of Geographic Information Science, Geographic Analysis, and the Annals of the Association of American Geographers. He has published 15 book chapters and 4 co-authored or co-edited books. His research has been supported by the National Science Foundation, the National Institute of Health, the Cubes company, and the Sound Software company. He received his PhD in geography and a master degree in statistics from the Ohio State University, and the master degree and the bachelor degree in geography education from Seoul National University. It's a great pleasure to welcome Professor Chun.
Right. Thank you, Professor Wang, for a nice introduction. Let me share the screen here so that you can see my slides. So if anyone can confirm that you can see it, okay, that's great. So I'm Yongwan Chun. I'm a professor at UT Dallas, and then today's topic is that uncertainty in spatial analysis. I'm going to focus on 3 subfields, which are visualization, measurement, and modeling. Okay, so this is outline. We're going to start with the introduction, and then we're going to move on to visualization about uncertainty, and then the next topic is about the spatial autocorrelation measurements with uncertainty, and then the third is the spatial data modeling with uncertainty. So basically, we're going to have some slide about the measurement data models, and then also kind of mixture of spatial correlation patterns, different patterns. One is positive, and then the other is negative spatial correlation. So that is more related to model specification issues. So introduction. So we know that our data is not perfect. We know we have error in our data set. So every single observation is a topic of uncertainty. Geography of error dates back to decades. So one of the early work in geography and in GIS is done by Goodchild and Gopal. They signify a more concerted geospatial research effort. So we need to address uncertainty in our data set better, so we can have a better results and then more reliable conclusions out of our data analysis. So it also connects well to popular applied statistics. So if you remember a kind of introductory level of statistical courses, we deal with the means, but also we deal with standard deviations, marginal errors, and so on. So those are really, really popular. We need to take a look at them so we can measure with a reliability. Okay, and in GIS or geography domain, spatial interpolation method is one quite popular tool, and then the kriging is one of the best tools that we have for spatial interpolation. And then when we teach is kriging, okay, we say that kriging is really great because it produces uncertainties for predictions, right? As well as predictions. So not only interpolate the surface, but also it produces errors. So that's great aspect of spatial interpolation. So this presentation will focus on some research topics related to uncertainty, along with some recent papers that I worked, that I published with my colleagues. So errors in spatial data, it's really, really inevitable. But there are two aspects. One is that we can have locational uncertainties. So when we have, for example, point location, and then we are not sure if the location is 100% true, right? Often, for example, when we have a GPS data set, we are not sure the GPS XY coordinates are correct. Maybe we know that there are some errors, right? So location error is one thing. So more formally, we can say that geometric inaccuracy of locational tags, and it happens a lot. And then there are methodologies to model such locational errors. So for example, one of them is an error ellipse model. So when we have true location for XY coordinates of points, and then observations are around those true locations. So often it happens with a form of ellipse around the true location. Okay, and then the other is attributes. So when we work with the social science data sets, the location tags are important, but also we want to take a look at the attributes which are attached to those spatial objects. So inaccuracies of reported quantity is often a topic for attribute uncertainties. One great example is American Community Survey, ACS data. After 2004, the Census Bureau started releasing ACS survey data with margin of errors. But basically, the sample size is much smaller than decennial census. They wanted to make sure that this information contains some errors. Okay, so in this presentation, I'm going to focus on attribute side rather than location side. So some sources of errors in attributes, one of them is measurement error. When we have direct observations, we may have the errors in terms of the measured quantity. Okay, so that's the one. We measure our height, but we are not sure that our height is 100% correct, right? So maybe we just truncate after one or two numbers after the decimal point. So we still have maybe affordable or unaffordable errors. And then next one is the specification error. So when we deal with modeling, for example, regression models, we may end up with incorrect assumptions for distributions, for example. So when we deal with the count data set, often we assume that those count data follow a normal distribution if you run linear regression, which is often inappropriate. Then it might be a one source of specification error, right? And if you miss one relevant independent variable, that is also another example for specification error. And then third is the sampling error. So we're going to use a subset populations. So by using samples, always our observations are subject for uncertainty. So this is an example about American Community Survey. And then if there is anyone who is not familiar with ACS data, for example, here in this figure, I'm not sure if you can see my mouse point. We have population group, right? So under 5, between 5 and 9, between 10 and 14, and other groups here. And then we have number of people. These are estimates because we have a small sample, and out of small sample, we estimate it. And then they report this margin of errors. So for example, here for under 5, we have estimate value about the 53,000, and the margin of error is really small. But if you see another population group like a 10 to 14, the margin of error is really, really large compared to the other one, right? The margin of error basically represents 90% of the confidence interval. So using 1.645, which probably you're familiar with already. So 95% confidence interval in stack course, but that's in the case we use like 1.96, something like that. And for 90%, we use 1.645. So, and then SE stands for standard errors. So using this equation, they calculate margin of errors, and then they report this margin of errors here. Okay, so some cases estimate is of 37,000 for block group 1 in the table, and the margin of error is quite large. Still, it may be between like 15 or 17,000 and then 57,000, one number between this huge range. So there are a number of literature papers which address research topics in uncertainty. The one that I published with my colleagues is in the book chapter. It's a book chapter in a uncertainty book, and then it addressed that we have a unique challenges about visualization of uncertainty. And then also we have some spatial patterns with the uncertainty, spatial pattern measurements. Spatial modeling with uncertainty is going to be also a challenge. And other times we deal with the spatial data aggregation. So we deal with a polygon data set often, and then the aggregation has an impact on data itself, and then also the analysis of the data sets. And then spatial metadata for data quality probably is crucial to communicate with the people more appropriately about the uncertainty. So here in this presentation, I'm going to focus on these three topics, okay? Uncertainty visualization and spatial pattern measurements and spatial modeling with uncertainty. The first one, so uncertainty visualization. So we have done a lot. Geographers make maps a lot, and then easy way to show uncertainty is to make two maps and then place them side by side. So for example, in this example, in this figure, we have median income for counties in Texas on the left side, and then we have a coefficient of variance on the right side. So basically, the relative size of variance compared to the mean of numbers. Okay, so if you see that if we have a dark colors, so basically we have more variability. If you have light colors, we have less variability. So by doing that, we can say that okay, some numbers are more reliable than other numbers. Okay. And another approach, quite simple approach, is that we're gonna combine these two sets of representations into one piece. So here we have a median income in the core path map colors, and then we have the hatching symbols for uncertainties. Okay, so there are a number of papers address these issues, and some papers claim that the bivariate mapping, which is the combined cases, is more efficient than the side-by-side mapping here. But readers do not need to, because readers do not need to switch their focus between two sets of maps. Okay, but sometimes it is not quite straightforward to provide the two sets of information simultaneously. So probably we need to do some more work, and then some combinations works better than other combinations. When you do that, probably we can consider two things in the mapping. The one thing is that different mapping techniques should be used for these two sets. So one it really depends on the types of attributes. Core path map is one technique, and a proportional symbol map is another technique. And so one more thing is that we may need to understand the characteristics of our attributes. So some values are like summarized or standardized values, like population density, and then others are raw count. So rather than population density, we can use just raw count of population. So considering those characteristics of population or attributes, we may use different, more appropriate symbols. The one more thing is that visual integral symbols and then or separable symbols. So if you take a look at these two, and then on the left side, we have like a nowadays very common in ArcGIS Pro, that we have one variable along with the x-axis, and then another variable along with the y-axis, right? So two sets of variables are integrated into one, we can say bivariate color symbol. So these are more like integrated into one. And then the other set, we have colors for attributes and the hatching symbols for uncertainty. So they are separate in the visualization. So often this separate representation is much better for bivariate mappings. And when we do bivariate mapping for uncertainty. And still, we need to consider visual variables very cautiously. And so here, we published a paper, and then we have two different types of attributes: standardized one, like a population density, unstandardized one, raw count of a population, and then we can use different thematic mapping techniques. Okay, and then additional visual variables for uncertainty representation. So these are some good combinations, and then based on our experiments. So we implemented this idea using our ArcGIS engine components, and then this is available for free on GIS GitHub website. And then if you see one case, we have overlaid the symbols on the core path map. So we're going to have core path map for attributes, and then we're going to have a different spacing or different sizes for core path maps. Okay, that's one example. So here on the left side, the spacing doesn't hide much this core path map, but when we see this proportional symbol map, sometimes we have polygons which are much hidden by symbols. But still, this is one of the better options than other combinations that based on our experiments. The second is same idea. So we're going to have saturations and value for uncertainties. Point symbol size represent the attributes, and then different values. Small error and a large error. Light color represents small error, and dark color represents large errors. So on the right side, that map shows the two sets of information, and on the left side, saturation is used. So when we have a pure color, and we're going to say this is rather small, represents small error, and then when you have a more impure colors, then pigment level is not that great, then we're going to say that this is a high level of uncertainty. But often saturation isn't a great visual variables. Although I have the slide about the saturation, still I think that the value is much better option. And then different techniques, like see, we have point symbols and circles, and then this red line represent the attributes, and then around the red line we put the some uncertainties. Okay, so using, for example, the marginal errors around the estimates, and then bar chart might be a little bit more straightforward. So the boundary between the red and then blue rectangles is an estimate value, and then around the estimate value we have uncertainties. So when you have thicker symbols, we're going to have thicker boundary, and basically they represent the higher uncertainty levels. So that was the first topic that I have about the visualization. Okay, and the second topic about the visualization is map classification with uncertainty. So we know that map classification is automatically done in ArcGIS Pro if you choose an option, right? But when we do it, usually we just consider estimate only, not uncertainties. Uh, but one question is that if we have two values are truly statistically different, or they are from a single distribution. Okay, so that is one thing that we may question about. So if you do, maybe you want to consider uncertainty of the data set. Again, so ACS estimate with a large MOEs might be different from just when we consider estimate only. Okay, so that is an association to uncertainty in map classification. So one measure in the literature is that separability measure. So David Wang and his colleagues developed a separability measure, which is defined with this. So basically, he take a look at the mean and then errors for each ACS estimate. For example, we have estimate, which is mean, and then MOE. From the MOE, we can calculate the standard errors. So for each single observation, we can draw this bell-shaped curve, assuming that they follow normal distributions. So when we have two numbers, x1, x2, they are different, but when we consider their uncertainty levels, probably we can clearly say that their distributions are quite different, so they're not from a same distribution, or their observations are quite close considering the variability of those observations, then it might not be easy to say that they are from a different distributions. So by using this two, let's say the two mean difference tests, they calculate a separability measurements. Okay, so it is basically based on the two mean difference test. So once we have the means and the standard errors, they calculate this number and then calculates the probability based on the normal distribution, normal curve. And when we have many observations, and then we're going to have class A, class B, class C, class D, and then we can measure kind of the separability between class A and B. So one thing is that we're going to have one observation with a distribution, and then another observation in B, a distribution, and then compare the calculate the separability. And then among different pairs between observations in A and B, the smallest value might use the class separability between class A and then class B. Okay, so that's one map they developed, and it's Cedar Iowa counties. So on the left side of the legend, we see some class separability measure, and on the right side, we see the estimated values. Okay, so we only have estimated values in normal mapping, but on the right side, we see that how confident we are about the actually separability of classes. So big numbers show that, okay, they are quite different, and small numbers show that they tend to be similar considering uncertainty. So rather than that, well, we may try to have map classification results using uncertainty in the formula of map classification. So one thing is that Cromley and Campbell, and they found that map classification is basically same as a shortest path problem when we have a network in ranked order. So the nodes corresponds to class breaks, and then arcs presents basically grouping of observations. So basically, when we have two class results, the one observation 1 to 4, it is they will go to one class, and an observation 5 will go to the next class. So that is the one. So we find kind of the shortest cost path with a different number of stops, breaks, then it is basically same as the optimal map classification problem. So we need to calculate, compute cost values attached to those arcs. And then once we have them, we just find the kind of the combinations with the minimum of the objective values. Okay. So we need to calculate cost value for each arc. And then one thing that we can use is that like a sum of deviations from group means. So each group we have kind of means, and then we're going to measure the difference between each observation in the group and the mean of the group. And then we sum them up, and we want to find kind of the result which gives the minimum the value of the objective function value. Okay. So we can set a measure that consider estimate and uncertainty. And then one thing that we did as a separability, as I introduced in the previous slide, there might be one other. And then we came up with another measurement, which is Bhattacharya distance, which is quite popular distance measure. So I'm going to introduce the Bhattacharya distance. It can be used either discrete distributions or continuous distributions. But when we have two normal distributions, and then it can be simplified with this equation. So the first side is about molecular variances. And then the second component of the equation shows that the estimate differences. So not only estimate differences, and then it also consider variances in the distances. Okay, so separability is one measure, and the Bhattacharya distance is a second measure. Then we can compare. So using these two measures, we calculate cost, and then we're gonna find a group. Okay, shortest path, which minimizes some of the within group measures. Okay, once we set that up, they can be solved with optimization, like a linear programming packages with Groby, Cplex, or other types of libraries are fine. The one demonstration is that we have one data set, which is 5-year estimate of median house income in Texas. Okay, so here the first map is a natural breaks, which is a default option in ArcGIS Pro, and the second map is the separability, original separability map. The one problem of the separability map is that many observations fall into one single class, and then other classes will have just small number of observations. So here we have 5 classes, and then probably one class has one observation, another class another observation, and then the many counties fall into just single observation. Okay, rather than that, based on our approach, separability measure, and then Bhattacharya distance based on the cost, we run optimal map classification approach, and then we have 2 different maps. So this is based on separability, and then this is based on the Bhattacharya. So again, if you just see these map patterns, they are quite different. If you ask which one is better than the other, sometimes maybe natural break maps are better than other types of maps. But if you want to consider uncertainty in your data observations, then I think that might be quite separated from the other method. So that's one approach that we developed. And then an interactive tool is available in the package that I gave you the link, GIT GitHub link. So one observation has this estimate, but has huge uncertainty, MOE level. So So sometimes it is hard that this value is really different from the neighboring values, right? So considering the uncertainty might give you different patterns in your mapping, which is one county in Texas. I think that it is oil field and there are only small number of people, and then the economy is great because of oil, and with a small sample size, yeah, it gives large MOEs. Anyway, so this is a representation of the classes based on natural breaks and then separability cost and then budgetary cost. As we expect that separability cost gives a smallest value, okay, when we calculate separability, and budgetary distance, it gives a smallest one. But if you see that the first column represents the difference between the counts, the smallest count for one class and the largest count for one class. So one class has like, let's say that one, and then another class has 258, then it gives like 274. So it's kind of range of observation counts. So it means that basically we have more kind of balanced distribution among classes with the other approaches rather than separability. So it's an issue of separability, the measurements and the mapping with the separability measurement only. Okay. The second topic is the spatial pattern measurements when we have uncertainty in our observations. So popularly, we measure spatial articulation using Morin's eye, Gear C, but we do not consider uncertainty in the formulations. Okay, but we know again MOEs of ACS dataset they have errors. Those errors are not uniform, random in space. It means that some area with higher errors and then other areas with lower errors. So these potentially have an impact if we consider different variability of observations. So their statistic results may not be reliable if we just disregard the uncertainty, the spatial pattern of uncertainty. Okay. So here, one example, this is 5-year estimate for Texas counties, so median household income. So let's, you see the estimate, and the right, you see uncertainty. And another map shows that if this is Dallas County, census tracts in Dallas County, Texas, we have income and we have uncertainty on the right side. Okay. So as you see that we have kind of formed spatial patterns, right? So errors are not spatially random or uniform. So we may need to consider different error patterns. So potential bias of spatial correlation measures is illustrated with this. So when we do kind of simulation experiments, we have estimate and the standard errors. So out of that, we found the normal distributions for each observations and the randomly draw numbers from each normal distribution, and then the major spatial autocorrelations. Okay. Without error consideration, we see that, okay, so we have Morin's eye on the left side and then Gears ratio on the right side. So we see that overall pattern, observation pattern is quite different from the histogram that we construct with the consideration of uncertainty. Okay, if you just ignore the uncertainty, it tends to show that stronger level of spatial autocorrelation. So this red bar represents spatial autocorrelation without consideration of uncertainty. Okay. So expanded the experiment a little bit more. So we use this SAR process, spatial autoregressive process. So this is observation, and then W is a spatial weights matrix, and then I is identity matrix, and then E is a spatial random, just random numbers. Okay, we embedded row values. The positive numbers represent positive spatial autocorrelation, and the negative values represent negative spatial autocorrelation, and zero basically no errors, right? If you have zeros, and then no spatial autocorrelation. So we have just non-spatial random numbers here. And then this SR process, with SR process, we randomly draw numbers, but we use this 10 by 10 hexagonal and 30 by 30 hexagonal and 50 by 50 hexagonal tessellations. So basically 3 different types of tessellations. And also the error level is another key factor. So to do that, we put the different levels of errors. Okay, so it is modeled from truncated normal distribution, and then the means are there, and then same levels of standard deviations was used when we draw random these numbers for the truncated normal distribution. So for total of 54 stats, so 9 raw values, and then 6 coefficient of variance values. So if you see that, so using these simulated numbers, random numbers, we measure spatial autocorrelation. So for example, here, let's go with the figure A. If we see, we have Murenzi values for each set, and then we put them with a box plot. So for each level of spatial autocorrelation, okay, and each level of CV, coefficient of variance, we have 1,000 numbers, and then those 1,000 numbers were represented with the box plots. Okay, so if you see that we have these box plots with a large range, right, as we have a higher level of spatial autocorrelation. Okay. But if you see these dots, red dots, which are connected, and then that is Murenzi without consideration of uncertainties. So if you see that these dots are quite leaning toward one side, okay? So for positive autocorrelation, it tends to be very close to extreme positive case among our simulated values. If you go to the negative spatial autocorrelation, this red dot tend to lean towards the negative side of extreme side of a spatial autocorrelation. So it doesn't follow kind of the middle levels. Okay, so it has some evidence that Murenzi without consideration of uncertainty tend to stronger, more positive side, more negative side, if you take a look at this map. Okay, so probably we may want to have a different idea to measure spatial autocorrelation with uncertainty. So one thing is that Bhattacharya distance was there, and then another kind of the measurement, which is based on Bhattacharya distance, is the Bhattacharya coefficients. You can think that this is a kind of portion of overlap between two distributions. Okay, so one normal distribution, another normal distribution, if you draw them into one piece of a plot, then they have large overlaps, small overlaps. Okay, so that's the amount of overlap. The Bhattacharya coefficients basically represents this. And then we expanded this Bhattacharya coefficients into the spatial context. So we use this similar formula with the Murenzi, and then we just replace the x and y, those numbers, with the Bhattacharya coefficients. So using this, SBC spatial Bhattacharya coefficients is defined, and then it basically have the same structure as the Murenzi. So it ranges from 0 to 1, and then high value indicate a high degree of similarity with the spatial neighbors. So we conducted another simulation, so 1,000 replication for each set, and then we get the numbers, okay? And we also get this variability uncertainty. But if we calculate the Morin's I or Garcia, which are popular spatial error correlation measures, we do not consider errors. So every box plot for the same category has basically same variability, okay? Which, yeah, because we didn't consider errors. But here with SPC, we see that different patterns, right? So the mean increase as rho, which is level of spatial error correlation increase, and then that's one pattern, and then it is affected by the error levels as well. So that is probably we may not say that this is a better measurement compared to Morin's I or Greer C, but this is a different measure when we consider uncertainty in our observations. So empirical data set, we had a same median income and then the Hispanic population sizes and spatial error correlation based on Morin's I and the Greer's ratio. We have these values. And then if we consider this different variability uncertainty, we see that we have higher SPC, spatial bacteria coefficient levels. Okay, so based on permutation test, we see that the observation is quite different from the reference values. Okay, so these are two topics, subtopics about visualization, and the next one is spatial modeling components. So spatial modeling with uncertainty, the one popular model in stats literature is the measurement error models. So there's a popular book about measurement error model by Fuller. It is also called error invariant models. Okay, it has not been utilized in spatial data analysis much. So considering that we have observation Z, okay, this observation is combination of true value X and then some sort of like an error, this new, okay? So always we have observation with true plus or minus the error, okay? So if you run the regression with the Z, it is different from the running regression with the true values. So this measurement error models has been developed to consider these errors that we have in our observations. So if we do not consider those errors, linear regression results will be biased. And then the popular approach to mitigate the problem is that we're going to introduce instrument variables, okay, additional, let's say the independent variables, or quite not, yeah, same, but we can basically say that we're going to have additional variables, instrument variables. And then a complexity level increases if we deal with the non-linear cases. So linear cases is relatively simple, but the non-linear cases, we have quite complex situations. Okay, and then other estimations are available, generalized least square rather than just maximum likelihood estimation or other types of method. And then one of the popular ones is the Bayesian models. So we can actually improve to add the data errors in our Bayesian models. Okay, so I'm going to introduce Bayesian approaches. Probably you guys are very familiar with the Bayesian models. The Bayesian, based on the Bayes theorem, so posterior distribution is proportional to process models, and then the parameter model, which is the prior parameters, right? So, but we can introduce data models with the measurement errors. So the posterior distribution is proportional to data models, process models, and then the prior parameters. Okay, so if we do that, so we're gonna have this additional cases. So we observation Z is conditioned on the true value of X and then error nu. Okay, for process case, for example, here, if it is a Poisson distribution Poisson process, this Y observation is conditions on the mu, and the mu is modeled with the population, and then relative risk, and then the relative risk is modeled with this regression context, right? And then the parameter model, we're gonna have the distributions, the prior distributions for those parameters. So we just expand one more level from the regular Bayesian approaches. Okay. Some simulation experiments. We use the counties in state of Indiana, and then those covariates are here. The percentage of households with the gross rents is 30% of or higher of their income, and also percentage of house with a single parents of minors, and then also age groups. So we use kind of nominal coefficient levels, which are 0.03 minus 0.12, 0.18, and then drawing y from a Poisson distribution with a mu I as a parameter, and then the mu I is scaled with this. Okay, so we have nominal levels, right? So we draw the numbers, and then we construct the z with x and nu, which is basically standard errors of ACS estimate from the ACS data. So by doing that, if we have parameter posterior distributions and conditioned on y and x, y and true value, or y and z, and then additional error models, we have a difference, right? So here, the 95% coverage basically means that the true value is in the 95% credible interval. And then out of 1,000 cases, okay, we have many cases, this amount of cases within the 95 credible intervals. Okay. So by doing that, we can have basically it's very similar, right? But we have different posterior distributions. Okay, so it doesn't mean that small RMSE is correct or better. Okay, they do not consider uncertainties. So with the consideration of uncertainties, we may have a little bit larger distributions. Okay, but still we consider uncertainty in the models. Okay, and then based on this, we can construct statistical decisions whether or not we're gonna reject or accept a null hypothesis. And the next one is that uncertainty in spatial autocorrelation specifications. So most spatial models focus on positive spatial autocorrelation, but often we see that some components are negatively spatially or autocorrelated. Okay, so empirical data sets, we often have only positive data spatial autocorrelation, but still this is one subject that we may want to explore further. Okay, so it is limited because popular spatial models do not have kind of defined configurations. It only has one single number to measure level of spatial autocorrelation, which is rho here. But negative spatial autocorrelation often is mixed with the positive spatial autocorrelations. Okay, so for example, if you take a look at Moore and scatter plots, we have first observation in the first and the third quadrants. They represent positive spatial autocorrelations, and observations in the second and the fourth quadrants represents negative spatial autocorrelation. So these two components are mixed in the data process. So one technique which can combine, incorporate these two sets of spatial autocorrelation component is that eigenvector spatial filtering approach. So here we have C, which is the spatial weights matrix, let's say the binary 0, 1 spatial weights matrix. The M is a projection matrix, which is really popular in linear regression, right? So M times the C and M. So using this transformed spatial weight matrix, we can generate eigenvectors. Okay, those eigenvectors represent unique level of spatial autocorrelations, and also they are not correlated, and they are orthogonal. So introducing those eigenvectors into linear regression or nonlinear regression, we can isolate spatial autocorrelation components, okay, using this term. And so we can simply expand linear regression technique or nonlinear regression technique by adding these eigenvectors into the model. So that's the basically backbone of eigenvector spatial matrix. So often people limit to use positive eigenvectors, okay? But having negative eigenvectors would help us to explore further. So one example here, we have 20 by 20 square tessellations, basically 400 polygon, let's say that. Okay, each square is a polygon. And so we have 400 observations. And then if you make map with eigenvectors, okay, those eigenvectors, again, they are orthogonal, uncorrelated, and they represent a underlying level of spatial autocorrelation. This is the first eigenvector, which represents the largest positive spatial autocorrelation. And then this is second eigenvector. Because of the tessellation characteristics, which is this square tessellation. So if you just rotate 90 degree, then you're gonna have another pattern, right? So that's basically this one. That's the second eigenvector. And then we're gonna have third, fourth, up to 400 eigenvectors. Okay, if you see that 400 eigenvector, and this is the most negative spatial autocorrelation pattern given this set tessellation. Okay, so in the middle we have a eigenvector whose spatial autocorrelation level is almost zero. It's actually zero. Okay, and from the first one to 195, all these are all positive eigenvectors. From 197 to 400, then these are all negative eigenvectors. So you're going to utilize all of the eigenvector space. So if we have 400 observations, polygons, then we're going to have 400 eigenvectors. Among them, some eigenvectors which are really close to zero spatial autocorrelation, we're going to exclude them, and then the other eigenvectors can be utilized to isolate the spatial autocorrelation in the models. So I'm going to show one thing, so one example. So here is that age-adjusted breast cancer cases in Broward County, Florida, from 2000 to 2001. And then Poisson model specification is used. And we ran standard Poisson model and then ESF, eigenvector spatial filtering model with positive eigenvectors only, and the same model specification with the positive and the negative eigenvectors, both sets. So this observation itself has high level of spatial autocorrelation, right? The Z-score of Morin's eye is like 6.48, so it's positive, highly strong positive spatial autocorrelation. And then this is the coefficients of these three models: standard Poisson regression model, and then the ESF model with only positive eigenvectors, and then ESF model with both positive and negative eigenvectors. So let's start with Morin's eye on the residuals. Okay, the standard Poisson model, it shows that significant level of positive spatial autocorrelation. Okay, the test is done with the one-side test. So it means that so it shows that positive spatial autocorrelation. And then if you run the second model with only positive cases, the Morin's eye value, the p-value is very close to 1, which means that it's an opposite side. So it basically means negative spatial autocorrelation in the residuals. Okay. And then theoretically, if you have 0.5, that's kind of middle ground between two sets of autocorrelations. But here it's quite close to the middle ground, right? So Morin's IP value is quite close to 0.5 compared to the other two. So we can say that this doesn't suffer from any type of spatial autocorrelations. Okay, and with considering both types of autocorrelation, the model specification is better, and R square is better. AIC value is smaller, and then two independent variables have a changes of significance, right? So the female 45 or less and a college degree, they have opposite patterns in the result. So if you compare the non-spatial model, which is the first one, and then the spatial model, considering only positive autocorrelation, which is the middle one, we see the difference of statistical decisions. At least the number changes, but distance doesn't change, right? But considering negative spatial autocorrelation in addition to positive spatial autocorrelation, we see the clearly opposite statistical decisions for these two variables. Okay, so this is a different specifications for spatial models. No spatial autocorrelation, positive spatial autocorrelation, and then both positive and negative spatial autocorrelations. Okay. So spatial components. So we see the linear combinations of all positive eigenvectors. So that is positive autocorrelation components in the model, and then here is negative spatial autocorrelation components, right? So we see the more cluster patterns, more kind of regular dispersed patterns. Okay, so we have additionally these patterns in the model, and then we have different statistical decisions. So concluding, I discuss about kind of the uncertainty information for spatial data with the ACS. This is really popular nowadays. MOE error data sets are available for observations, and then we need to have a good understanding about the uncertainty to enhance our spatial data analysis. So I discussed these three areas with the publications that I did with my colleagues. So Dan Griffith at UT Dallas, David Wang at George Mason, Barry Cronenfeld at Eastern Illinois University. And then the other three were my PhD students. Now they're on the PhD. Okay, this is what I have. Do you have any questions?
Yeah, so we open to the questions currently. So thanks, Professor Chun gave an excellent presentation about this uncertainty in spatial analysis in terms of visualization, measurement, and modeling. So I'm wondering, like, you mentioned like a positive and a negative. So in what situations we use the positive, and in what situations we should use the negative, or because you are showing the map visualization very different patterns.
Right. When we deal with the spatial models, the spatial autocorrelation is summarized with one single parameter. So if you run spatial regression, we have row parameter, right? So it is summarize the information out of the whole range of spatial components. So with one parameter, within the computation, the positive and negative spatial autocorrelation cancel out each other, basically. So think about you're going to combine these two patterns, then you may have kind of random patterns. Okay, so if you suspect that you have some kind of process which potentially lead to negative spatial autocorrelation in your data generation process or in your observations, I think then you need to consider to incorporate the negative spatial autocorrelation components. But that's not clear much. But one indicator or tool that we can use is like Morin scatter plot. So when we have a chunk of positive spatial autocorrelation components and a chunk of negative spatial autocorrelation components, there might be one indicator that, okay, global Morin's you're gonna just summarize across these observations, but you may be able to divide this component into negative and positive size.
I see. So then also you are showing is these positive and negative, and also when running the first time and the second experiment, so they have the same number is because didn't showing the more digital decimals, or they just get the same number. You are showing that there are yeah, so for this one no, this one, like the eigenvector, the first and the second is the same number, is because you didn't show more digital decimal, or actually they just the same number, MC.
They are same because, you know, if you just rotate the first eigenvector 9 degree, then that's going to be the same because it's because of the configuration. So if you have more rectangular study area, then you're not going to have the same pattern. The first and the second will be different. But when you have square tessellation here, we have just basically same pattern with the two different sets of numbers.
Okay.
So that's the only kind of artifacts out of the tessellations.
Yeah.
Yeah.
So and also here is kind of see the one is the MC is 0. So usually that will be used or not for like the 0, this one.
So if we have this, okay, we shouldn't use it. If you go back to the equation, because of this configuration, so one vector is taken away from the identity matrix, the projection matrix. So if you are familiar with the linear regression cases, the projection matrix contains one vector, intercept term, right? So they're going to lose 1 degrees of freedom. So because of that, at least one vector contains 0 numbers. So that's the vector. Looks like they have variations in the map, right? But their variations are really tiny. So if I just round the numbers after maybe two digits after the decimal point, they're gonna be basically the same. So those eigenvectors should be excluded.
I see. So then the other is I saw you have for one the bivariate mapping, showing the map is showing like the median age, and also the uncertainty. It's very related. So which you can say for this uncertainty is also related to the contextual variables.
I believe so. For example, survey data set, they have more samples from one location with more population often. And then the population sizes are clustered in space. So contextually, there might be a potential factor. So we have more samples in one region, one clustered region, and a small number of samples in another cluster of regions. That happens a lot, actually.
So the sample size matters a lot.
Sample size actually matters because the MOE calculations by Census Bureau, they have number of samples in the formula, so it matters actually. Yeah.
So then the you are showing actually for ACS. There's one the county you are showing has very large these ME numbers. So that is more like representative for the whole ACS service data, or it's just a little bit extreme number for that you are showing like a Hamilton County.
Yeah, it's kind of extreme actually, because population size for the county is really small and the sample size is small, and then calculated MOE is large because of the small sample size. So we have estimates out of samples, right? But the variability with a small sample size is large. So that might be kind of factor that, okay, how confident about our observations.
So yeah, that's very interesting. So in terms of like this, how we use this ACS data for these different ME uncertainty, these indicators. So do you have like suggestions in terms of this ME? Should we choose like you introduce 3 different classification methods, natural breaks, and also separability, and also attach area, and that so. Do you have suggestions when we use the classifications for different sample size or different ME that numbers? How we should choose that?
I think that if uncertainty of your observations matter, you may need to consider a methodology which incorporates the uncertainty levels in the procedures. Survey data, often we encounter such cases. So we wanted to develop approaches to consider estimate as well as the uncertainty levels of those estimates. That's the one. So it really depends on your context analysis or contextual information for your data analysis, and then also your observations themselves. If you think uncertainty matters, I think that maybe you can try these methodologies that we developed. But often many people still do not consider them. So at least I think that you need to aware that your statistical decision on your data analysis might be different when uncertainties are considered, factored in your data analysis. I think that that's the kind of bottom line that I want to carry. Probably we need to explore more, study more, so we can say that in what context we should consider uncertainty, or we can just ignore the small amount of error when we deal with the spatial data analysis. So it needs further study, I believe.
So then for these different methods used, which means because actually when you consider uncertainty or not consider uncertainty, they have very different patterns. So then what you're saying is actually is not not always we should consider uncertainty. It's only in some context situation, then we should because I saw you have one map is showing when you consider uncertainty, it seems all the map is same except individual county is different classification. That map.
Like this.
Yes, this map.
They look similar, yes.
The last map.
This one?
Yeah, this map.
So David Wang, he wanted to have a mapping result for separability. Okay, so when he made a map, and then visual balance is not achieved at all. Because when we consider distributions of each observations and the overlapping portions of those numbers distributions, and we not often very confident that one is different from the other. Because if you take a look at each individual observations, they are, let's say that distribution do not are not quite well separated from neighboring observations. But think about it, this one on the bottom and the next one, their distributions are quite overlapped, right? So nice separations based on their configuration happens only like one, okay, small number of observations, like one observation on the top, and then some observations on the bottom. So that probably sometimes that is useful for some people, kind of because they give this result gives kind of confidence levels, okay, and the people feel that it is very confident that the one class is significantly statistically different from other classes, but that's just confidence levels between classes. But we wanted to have classification method considering this mean levels and then the standard deviations or uncertain levels. And although some are not quite well separated, like a natural break method. So we wanted to kind of clusters considering mean and MOE errors simultaneously. Does that make sense?
Yeah. So if in that case, do we have like this some like a test or the index we can use like to decide we should choose this consider this uncertainty or this separability or measurement or the Bhattacharya methods.
I don't think we have just kind of one single number to make a judgment with based on, but we'll probably at this moment we need to take a look at the observations and then visually inspect their uncertainty levels, and then probably we can consider or just ignore and then compare two sets of results, and that might be the practice. I don't think that we have just one single value which gives a definite classification between should or should not consider uncertainties in our data models.
Okay, I see. And for this one, is extension for ArcGIS or it's used in?
It's a standalone package. We developed the package using ArcGIS engine. So if you go to the website, you can download the package. Let me go back. Yes, this is the URL. Yes, the sar.github.io, and then
so this tours actually is can download from there to use for these different uncertain measurement.
Yeah, and then also ESF eigenvector spatial filtering is implemented in this package as well.
Oh, okay. Thank you so much. It's very people. This very useful and helpful talk to introduce how to integrate uncertainty in different contexts. Usually we give applause to the speakers at the end. Thank you so much.
All right. Thank you so much. Thank you. Thank you for having me.
Yeah.
Thank you, Riley.